Hey students, welcome to lecture number 4 of Linear Algebra 2. So today we want to talk about determinants, which are a really important subject in linear algebra. And what we want to do today is, if we start with some square matrix A, so square matrix, which means it has the same number of rows as columns, square matrix. Then we want to assign to it a number which is a determinant of this matrix. And this will be a real number. And these determinants, they have a lot of nice properties. And one important property of these numbers are, for example, that they tell us when this matrix A is invertible. And the statement is that a square matrix is invertible if and only if its determinant is not 0. So this will be one nice property why we are interested in determinants, to see if A is invertible without actually calculating the inverse of A. But we will also have different other applications. For example, we'll see that the determinant of a product of two matrices will also be just the determinant of the first matrix times the determinant of the second. And this will also imply that we can assign a determinant to a linear map. So last time we talked about linear maps and the matrices attached to them. So if I have a linear map F from V to V and I choose a basis, let's say I have two different bases of this vector space V, then last time we learned that we can attach a matrix to this linear map, for example, with respect to the basis B1, and we also could choose the basis B2, and these gave two different matrices for this one linear map F, but we will see that the determinant of these two matrices are actually the same, and therefore we can really speak of the determinant of this linear map F. And then we will also see that this linear map F is invertible exactly when this determinant is non-zero. But today we will just start by defining what the determinant is of a matrix, and also for this we will need to introduce some notation. But first, you already saw determinants in linear algebra 1. So in the case 2, meaning if we had 2 by 2 matrices, in linear algebra 1, in homework 2, exercise 1, you showed the following. So there we had the 2 by 2 matrix A, B, C, D, and you showed it's invertible. Well, in this exercise you showed that the rank of this is 2, but then later we learned that full rank means it's invertible if and only if the number AD minus BC is not 0. And of course this will then, as we will see later, be the determinant of this 2 by 2 matrix ABCD. And also, using this determinant, we were able to write down the inverse, which we did in the tutorial. So the inverse of this matrix ABCD can be written down explicitly by taking 1 over the determinant, which is a number, times the matrix D minus B minus C A. And you can check that if you multiply this matrix with this matrix, you get the identity matrix, where on the diagonal you still have the AD minus BC. So if you divide by this, you get the identity matrix. And of course this just makes sense if the determinant is non-zero. So this formula shows this direction here, but also you showed the other direction. And this so this is a special case of this statement here, that if the determinant is non-zero, then this matrix is invertible. Okay, so before we go into the determinants, I want to talk about the concept of proving things, because this we will do a lot of times when dealing with determinants. And some of you may be already familiar with this, meaning the what I want to talk about is the mathematical induction. So we want to prove things by using induction. And what is the general idea? So the general idea is, so Pn now is a statement which depends on some natural number n. And the goal will be to prove that this statement is true for all n. And for this, the idea of induction is that there are two steps to do so. So there are two steps. So the first step is the base step. And in this, one will show that the statement Pn is true for n equals 1. The base step, the idea is show P1 is true. And then the second step is the induction step. Where you assume that this Pn is already true for some m. So assume Pm is true for all m strictly smaller than a fixed n. And then what you want to show is that from this you can follow that Pn is also true. And if you do this, then you will see that if you combine this, you will see that you can show that Pn is true for all n. Because in the first step you show P1 is true. So you show P1 is true by number 1. And then by induction step you show that P2 is true. And then again you'll see that P3 is true and P4 and so on. Because here, this is of course 2. So this is always the induction step where you assume that the ones before are true, and then you proved here that if the Pm's are true for smaller m's, then you can show that Pn is true. And since you also proved the beginning here that P1 is true, you will get that this Pn is true for all n. And one standard example, or maybe first one remark. So sometimes you will have statements Pn where you don't want to show that this Pn is true for all n greater or equal to 1. So sometimes you want that this is just true for the case for n greater or equal to 3 or greater or equal to 4. But then you can also do this by just changing the base step. So there you can then just show that Pk is true. So you start always with the first one you want to show. And then here you also assume that in the induction step that is true for all m greater or equal to k and smaller than your n. And then here you start with k, and here you have pk plus 1, and so on. So you also get that this is true for all. So here you will get that Pn is true for all n greater or equal to k. So now let's do one explicit example. And one standard example is the following. So Pn is now the statement that the sum of the first n numbers can be written as n times n plus 1 over 2. And we now want to show that this statement Pn is true for all natural numbers n. So what will we do first? So the base step. So the case n equals 1. Well, what is this when n is equal to 1? So in this case, this is just 1 times 2 divided by 2. So this is just 1. But 1 is also the sum of the first number, 1. So this is just 1. And therefore, the statement P1 is true. Okay. And now, the base step. So now we want to assume that this statement here is already true for, so assume Pm is true for all m strictly smaller than some n. And now we want to consider the statement Pn. So we want to see what is the sum from I goes from 1 to n of I. And we now want to show that this equals this here by using that this is true already for smaller n. So in this sum here, a sum from 1 to n is of course the same as taking the sum from 1 to n minus 1 plus, and then takes a case where I equals n. In this case, this is just n. But now, this sum here is this sum here for n equals n minus 1. So we know here, so the statement Pn minus 1 is that the sum I goes from 1 to n minus 1 equals n minus 1 times n half. Because this is just a statement here with n going to n minus 1. So we assume here in the induction step that Pm is true for all m smaller n, and therefore this Pn minus 1 is true, and therefore we can use this here, and therefore n plus, and this sum we can now replace by n minus 1 times n over 2, and bring this on the same denominator. We get this is 2n plus n squared minus n over 2, and this is n times n plus 1 over 2 after factoring this here. And therefore we showed that Pn is true because now we have the statement that this sum equals this, so we have Pn is true. And therefore this Pn is true for all n because it's true, because P1 is true, and also if we assume that Pm is true for m smaller n, we show that then also Pn is true. Okay, so this is one simple example, and in the homework you will do 3 exercises by using this induction, and on the internet you find thousands of examples where this induction is used. Good. So now we can start with the main topic, namely with the determinant of a matrix. And before we define this, we need to introduce some notation. And the first one is what is called a pattern. So a pattern in an n by n matrix is a choice of entries. So I choose different entries of this matrix such that I choose exactly one entry of each row and one column. And the pattern we will denote by P. So it's a collection of entries of positions in the matrix. So it will be some tuples I1, J1, I2, J2 up to IN, Jn, where these i's are the position of the row, and this indicates the column. But let's just do an example, and then this becomes clear. So let's start with the case n equals 2. And now we want to see what are all possible patterns of this matrix A here. So the first pattern, so I need to choose an entries such that I have an entry exactly in each row and each column. So here what I can choose is this position and this position here. So let's say the pattern 1 is I choose the entry in the first row, first column, and in the second row and second column. And another way I can choose a pattern is I can choose this one and this. And this, so pattern 2 would be I choose in the first row second column and in the second row first column. And these are all possible patterns. And you also see that if I have a 2 by 2 matrix, these are the only possible choices, because I cannot choose 3 entries, because then I would have 2 choices in one row or one column. So the number of patterns, so the number of entries in a pattern of an n by n matrix is always n. But now let's do a bit more interesting example, namely the case of 3 by 3 matrices, and let's see how many different patterns we can choose here. And so let's start with this one. So I can choose this entry, and this entry. So this is a pattern because for each row and column I choose exactly one entry. So the pattern P1, first row, first column, second row, second column, third row, third column. And next one, not this one. So let's, for example, choose this entry, and yeah. Oh, this I don't want to do. I want to choose this one, and this one, for example. So P2. So I choose in the first row, second column, second row, third column, third row, first column. And now let's choose this one, and this one. So this is P3, first row, third column, second row, first column, third row, second column. And now, but these are not all possible choices. So here I just drew the matrix twice, so I have more room to draw. So we could also choose, for example, this one. Or maybe I choose the same as in the lecture notes, so I don't get confused. So it's, oops, this one, and this one. So first row, first column, second row, third column, third row, second column. This is one possibility. And P5, for example, this, and this. So first row, second column, second row, first column, third row, third column. And last possible choice is this one here, P6, first row, third column, second row, second column, third row, first column. And you can check that these are all possible choices of patterns for a 3 by 3 matrix. And I hope it becomes clear now how this works. So in here we had 2 possibilities, and here we have 6 possibilities. And in the homework you will show that the number of patterns, which we will rename in a second, corresponds, or is exactly given by n factorial. So here it's 1 times 2 times 3, and here it's 1 times 2. And in the case n equals 1, it's just one choice. Good. So now some new word. So we saw that for each column we need to choose, for each row we choose exactly one column, and this column we cannot choose again. So what we are considering are actually bijective maps from the set 1, 2 up to n to itself, And these bijective maps are called permutations of this set. And Sn denotes the set of all permutations. And then we see that a pattern can be written like this. So for the first, so I choose a permutation, sigma, in Sn. And for the first row, I choose sigma of 1. So this gives one of these columns. And then for the second row, I choose sigma of 2. And since this sigma here is bijective, we see that in particular it's injective, which means that sigma 1 and sigma 2 cannot be the same, which corresponds to the fact that in a pattern I cannot choose the same column twice. So this I get up to n, and here sigma of n. And you see I will get all columns because this map is also surjective. And therefore you see that patterns of n by n matrices are in correspondence with permutations of the set 1 up to n. Because each permutation gives a pattern, but also if you start with a pattern, you can get a sigma by just reading off what is the second entry here in these pairs. Okay, so yeah, one example. So let's choose one of these patterns here. Which one is nice? So no, this I didn't want to do. Let's copy this. So there's one way to visualize these permutations. So for example, in this pattern here, so let's draw it like this. I have the set 1, 2, 3, 1, 2, 3, and the map sigma, which corresponds to this pattern here, is that sigma of 1 equals 3. So sigma is a map which sends 1 to 3. Sigma of 2 is 1, so it sends 2 to 1. And sigma of 3 is 2, so it sends 3 to 2. So this is the sigma corresponding to this pattern here. And this picture will also be useful in the following. So namely, there's another word. So the number of inversions of a permutation sigma denotes, which we write in for inversion of sigma, is the number of pairs I, sigma I, and j, sigma j, such that I is smaller than j, but the image under sigma, the sigma of I, is larger than sigma of j. And then we say this, the sign of a permutation sigma, which we denote by sign of sigma, is -1 to the number of inversions. So in other words, so this number here, I mean, what is this? This is either 1 or -1, and it's 1 if the number of inversions is even, and it's -1 if the number of inversions is odd. So and what does this condition here means? So this means, for example, in this case here, what are the inversions? So inversion means I need to find pairs such that the first entry is that, for example, 1 is smaller than 2, but sigma of 1 is larger than sigma of 2. So here, this image, so this 1 is smaller than 2, but the image of 1, the 3, is larger than the image of 1. And in this picture here, this just means that I have a crossing here. So if I count the number of crossings, this is exactly the number of inversions. So here, the inversion the number of inversions of this sigma is just 2. But in other words, we can also read this off in the matrix here. So let's copy this down and maybe remove the other patterns. So what does a inversion mean in this picture here? So that that we have this crossing in this picture here means that that this thing here, so in the first row we have the third column, and in the second row we have the first column. So this means that this one here is on the top right of this one. Otherwise it would be on the bottom right. Like here, for example, this is on the bottom right, and this means that that these two lines do not cross. So you can also count the inversions by look at the pairs, such that there's, in this case, a pink circle is on the top right of another pink circle. And here this is, for these two, this is the case, and therefore we have 2 inversions. So there are 2 ways to count these number of inversions. And then in this case you see that the sign of this sigma is in this case -1 squared. So this is just 1. And in general here, if you look at this in these examples here, or maybe first let's do this one. So here, let's draw the sigma. So 1, 2, 1, 2. So here this is just this, so no crossings. So here the inversion is 0 and the sign is 1. And here the sigma, let's make it red to make it clear. It's this. So we have 1 crossing. So the inversion, the number of inversions of this is 1, and the sign of this is -1. And if you do this the same here, then you will see here, maybe let's make a table, inversions. So for the purple one, all these are ordered on the bottom right, so I cannot find another purple one on the top right of this one and not of this one, and so on. So the number of inversions here is 0. For the green one, I can see that there's 1 on the top right, and here's another one. So the number of inversions is 2. And for the pink one we just did, 1 is there and 1 is there, so this is also 2. So the sign of these is 1, 1, 1. So here are the signs. They are all 1. And here in this one, for the green one, I get 1 circle on the top right, so the number of inversions is 1 there. For this brown or dark red one, the inversion is also 1. And for the orange one, I have 2 inversions. So the sign here, oh sorry, there are 3 inversions, because here I also have, this I also need to count. 3 inversions, so the sign is -1, -1, and -1. So here the signs are -1. And that's why I grouped them like this. Okay, so now we talked about patterns and permutations, which are basically the same. And for each of these permutations, we can assign a sign. And with this, we now can define the determinant of a matrix, because the determinant of a matrix is given by this formula here. So if I have an n by n square matrix A, then the determinant of this matrix is the sum over all permutations of Sn. And then what I take is the product of all entries of the places I choose of this matrix multiplied with the sign of the permutation. And for this, we do one example. So we had this example. So there were two possible, so let's even give them names maybe. So sigma 1 and sigma 2. So this S2 in this case just has two elements. It's sigma 1 and sigma 2. And the determinant of this matrix A is therefore a sum over all elements here. So there are just two summits. So in the case sigma 1, I have the sign of sigma 1 times, and now I take the product of all the entries of this matrix A at these positions. So here, in this case, I get the positions 1, 1 and 2, 2, so this and this. So here this is just A times D plus the sign of sigma 2 times now the entries at this position, so it's C and B, but we saw that the sign of sigma 1 is 1, so this is just AD, and the sign of sigma 2 is minus 1, because we have 1 crossing here, or in other words, we have one position here on the top right of the other one. So therefore we get minus BC or CB. And therefore the determinant of this matrix is really what we said in the beginning. It's AD minus BC. So and what you could do now is also do the determinant of this 3 by 3 matrix here. So maybe let's do this just for fun. So let's call this matrix A. So let's start with a positive sign once. And maybe let's even do this with color. So we need to see for each of these patterns, we need to multiply the sign. So here it's 1, so here we don't need to care. And then we need to take the entries of this matrix. So here in the purple places I have A, E, I plus, and now for P2 I have B, F, G plus, and now the pink ones C, D, H plus, well, that's all in this case. And now I take the one with a negative sign, so I need to take minus. And now I get the green one, which is A, F, H. So maybe I should also do this, because this minus sign is really the sigma here, so the sign, sorry. And which color is this one? This. So here we have minus, now the one B, D, I, and orange minus C, E, G. Okay, so you see the determinant of this general 3 by 3 matrix here is given by this explicit formula here. Okay, so next time we will start talking about these nice properties. So far we didn't see why this is true here. So why is a matrix invertible exactly when the determinant is non-zero? And also this property here and this we will do next time. And yeah, so see you then.